Hello, my name is Ben Moldenhauer, and I'm a graduate student at the University of Wisconsin-Madison under Dr. Matt Allen. Today I'm going to be presenting some extensions and generalizations that we've made to a method for determining instantaneous frequency and damping of a nonlinear response. This is part of a project that was done in collaboration with Dan Rotkin at Sandia National Labs. So computing instantaneous frequency is a fairly common signal processing task in a lot of different fields. This is because you can typically characterize a lot of key aspects of a system by measuring its behavior and looking at the frequency content in that signal. In structural dynamics, this boils down to measuring a response with transducers and characterizing modal frequencies and damping ratios. One of the methods for doing this is Hilbert analysis, where the instantaneous frequency and damping are calculated in terms of the derivatives of the amplitude and phase of the oscillating signal, which are estimated with the Hilbert Transform. So this can work quite well for signals that are mono-harmonic and periodic, but if these conditions are not met, significant noise can crop up into the amplitude and phase and then consequently be amplified in their derivatives. This means that a lot of pre- and post-processing can be required to clean up the frequency and damping results to get usable answers. So as an alternative, Goyder and Lancereau proposed a method that avoids this by directly curve-fitting frequency and damping values to the oscillating signal with a nonlinear optimization scheme. In this presentation, I'll give you a brief summary of their method and then detail some extensions and generalizations that we've made to it to make it applicable in more scenarios. So the method that was proposed by Goyder and Lancereau starts with this equation for a linear damped oscillation in free decay with terms for initial amplitude and phase and natural frequency and damping ratio. So then obviously this process is going to be functionally limited to modeling structural response with constant frequency and damping and no external forcing. Now you could implement this equation into a curve-fitting algorithm as is and get an answer, but you can simplify it a bit by manipulating the expression and making some substitutions. So first we'll use the angle sum trig identity to remove the phase angle theta from the oscillation term. Then we'll condense the scalar coefficients into these capital A and B constants, and also swap out frequency and damping for the alpha and beta terms. The strength of this new expression is that we only have to directly optimize the values for alpha and beta, since we can uniquely determine the best fit values for A and B through a simple linearly squared solution with the measured oscillation. So in practice, what you do is go along the time series and break it up into discrete segments and do this optimization in each one. And then you can use these expressions to back out what the natural frequency and damping ratio are from the optimized values of alpha and beta. The example that Goyder and Lancereau present in their paper is with this section of bandpass filtered time response from an experimental impact test. Pulling out the first time segment and running the optimization, they got this, where the black dots show the measured data points and the blue line is the curve fit result. By marching down the time series and pulling out the frequency and damping from each segment, they end up with these plots showing the nonlinearity in both as a function of response amplitude. So that's the quick version of what's in Goyder and Lancereau's paper. Now, to make sure that this video isn't 30 minutes long, I'm going to show you an equally quick summary of what we've done to extend those ideas. But if you're interested in seeing the details of the math, I have some dense slides that I'll quickly flip through at the end of the presentation, where you can pause the video and take a closer look. So first, we'll start by making the equation for our oscillation more general, where it has beta and alpha being time-dependent terms that control the amplitude and phase. A more convenient form for alpha and beta is to just take them to be polynomials in time with arbitrary order. And here we can note that if you make them first-order linear polynomials, it reduces to what Goyder and Lancereau used, where the constant terms are the initial amplitude and phase, and the first-order coefficients are the frequency and damping. After going through the same sort of manipulations as what Goyder and Lancereau did, we end up with an equation like this with a term for the optimization variables and another that is a linearly squares fit for the constants A and B. And then when implementing this in a nonlinearly squares algorithm like trust region reflective, it can approximate the gradient with central difference, but it will be much more efficient if you can define it analytically. So here is what you get when you take the partial derivative of the equation for the fit with its specific partials with respect to the alpha and beta variables shown there. And again, I'll show a more detailed derivation of this at the end if you're interested. And then a couple more things. So basically, if you FFT everything, you can do the same optimization, but in the frequency domain on the Fourier coefficients. The main benefit being that you can restrict the optimization to a specific frequency band and avoid noise or other oscillations. And I'll note that you can window the time signals to reduce leakage, but it makes fitting higher order polynomial terms more difficult. And then leading off that, you can use this process to fit signals that have multiple overlapping oscillations, where you can either fit them simultaneously or sequentially. Both ways have pros and cons, and it's sort of situational as to which way is better. So next, you can have exact representations for integrating and/or differentiating the fit oscillations, where the first step is to represent the fit as a complex exponential, and recognize that as alpha and beta are just simple polynomials, their derivatives are as such. And then say that you're fitting oscillation. Say that you are fitting acceleration. You can use that info to back out what the displacement and velocity would be. And similarly, if you're fitting displacement or velocity, you can use the derivatives of alpha and beta to find the other two response quantities that you don't have. And finally, you can directly implement Michael Feldman's free vibe and force vibe methods in terms of the alpha and beta derivatives. These give you frequency and damping of a nonlinear single degree of freedom system during free and forced response. And you can see that if we make the assumptions that Goyder and Lancereau did and assume that the force and the second derivatives are 0, these reduce to the expressions they gave for omega and zeta. Alright, so there's a quick overview of the theory, and now I'll show you some demonstrations of what you can do with that. The first example is from a dynamic simulation of a nonlinear finite element model that you can see at the top there. It's a 2D cantilever beam that's split in two along the middle, with friction effects defined at that interface. The pressure applied on the top and bottom near the tip makes this roughly approximate a bolted connection. The response we have from this model has the first two modes ringing down simultaneously and is plotted versus time and frequency in the figure. In this case, I'll fit the modes sequentially, and this animation shows how the process marches down the time series and performs the fit in each segment, where the orange line is the curve fit to the first mode, and the yellow is the residual, which is basically the second mode. In the bottom half, you can see the fit in the frequency domain, where the black dots mark which points are being used in the optimization, and the vertical black lines show between where it is looking for a peak to initiate the fit from. The main results of that fit are the frequency and damping curves for the first mode. These, along with the result from Hilbert analysis, are shown here versus time on the top and amplitude on the bottom. You can see that our direct fit from the optimization produces smooth curves, while the Hilbert result suffers from end effects from having to bandpass the signal and it not being periodic. And now we fit the second mode from the residual after fitting the first mode. Again, you can see that on the bottom how it is fitting to the marked Fourier coefficients, and the residual after this is about 4 orders of magnitude less than the modal response. And the frequency and damping curves for the second mode tell a similar story, where our optimization gives clear smooth curves while Hilbert has end effects. And here's a figure showing the resultant fits to mode 1 and 2 and how they overlay onto the original signal. And finally, this is what you get from just adding the two together. You can see that the residual under the peaks is about 5 orders of magnitude less, and in general the residual is more or less just numerical noise. The other example I have is with experimental data from the aptly named cylinder plate beam, or CPB. This is a test structure at Sandia National Labs that they've used for quite a while in substructuring and nonlinear testing experiments. You can see in the image that it consists of a beam bolted to a circular plate, which is bolted to a hollow cylinder. The interface between the plates and the cylinder is assumed to contribute most of the nonlinearity in the structural response due to friction between the surfaces. At the back, you can see that a shaker is attached at the end of the cylinder, which was used to excite the CPB with a variety of sine beats, where the response was measured by the accelerometers positioned over the surface. Linear modal parameters were found by curve-fitting FRFs from a low-level burst random test, and the linear mode shapes were used to modal filter the physical responses into a set of modal responses. To use force vibe, the force needs to be represented as a complex signal. To get that, we fit the signal that was measured by a force transducer between the shaker and the CPB. This is what the resulting fit looks like compared to the raw signal. It very closely captures the fundamental harmonic. And then this is the fit to the modal response of the CPP. You can see an animation of what the mode shape looks like up at the top. And the resulting fit to the response also closely captures the fundamental, where here you can see that the residual is basically just the higher harmonics of what we've fit. And these plots show the resulting frequency and damping from free vibe, force vibe, and the linear test versus time on the top and amplitude on the bottom. I included the free vibe result because originally the intent with this data was to just analyze the portion of the response that is in a sort of ring down after about 0.5 seconds when the shaker finishes actively forcing the cylinder plate beam. While this is only a pseudo ring down because the shaker is still connected to the CPB, we were just going to assume that the effects of the shaker connection would be negligible. These results show that while free vibe and force vibe are relatively close during this pseudo ring down, the damping is being overestimated by free vibe, probably due to the shaker being a sort of energy sink now. And also we can see that we seem to have decent results during the initial part of the response that is actively forced, since force vibe traces out consistent backbone curves during the ramp up and ring down. It's also noteworthy that the low amplitude section of the curves is converging towards the linear values that we have from the independent low-level test. So in conclusion, I gave a brief overview of the nonlinear, the original nonlinear system ID method that was proposed by Goyder and Lancereau to determine nonlinear frequency and damping ratios by directly curve fitting them to segments of a nonlinear oscillation. The original formulation is limited to characterizing free decay in segments where the frequency and damping could be assumed constant. So in this presentation, I detailed some extensions to this process that make it applicable in more scenarios. First, we can generalize the optimization to fit higher order polynomials to the amplitude and phase, allowing for time variant frequency and damping in each segment. Then I gave the analytical form of the gradient for our curve fitting equation, which can be supplied to the nonlinear optimization algorithm to make it more efficient and accurate. And you can transfer everything to the frequency domain and do the same sort of optimization, but on the Fourier coefficients in a specific frequency band and avoid noise or other oscillations. And this led to how we can fit signals that have multiple overlapping oscillations, either simultaneously or sequentially. And by representing our fit as a complex exponential, we can use the derivatives of the amplitude and phase to integrate or differentiate the oscillation. So if we fit acceleration, we can say what the displacement and velocity are. And finally, I gave representations for Feldman's free vibe and force vibe methods in terms of the optimization results, which yield the natural frequency and damping ratio during both forced and free response. Then I showed two examples of use cases where I first extracted frequency and damping from a ring down of two modes from a nonlinear finite element model, and also frequency and damping during forced response of an experimental structure. Some future work that I want to do is to keep trying this process on other forcing and response scenarios to try to find what more limits are to it. And I also have some ideas for changing how it breaks up the time signal into segments and marches through them, because I feel like the current process is pretty brute force and could be a lot more efficient. And now, as I said before, here's a sort of appendix with slides giving more details on the math and theory that I had to gloss over earlier. So this is going over expanding the amplitude and phase to be arbitrary polynomials. This is deriving the gradient of the optimization function. This is a bit about converting everything to the frequency domain. These are just some points about fitting multiple oscillations. This goes over integrating and differentiating the fit oscillation. And finally, this is a derivation for Feldman's free vibe and force vibe methods in terms of the notation that I've used throughout here. And that's all I have for you. Thank you for taking the time to listen to this recording, and I hope to hear from you in the Q&A.